So I just finished recording this video. It took like a half an hour to record it. It was this big long video working through all these examples that you see in front of you. And I went and I stopped the recording and I got this error that said like, sorry, the program unexpectedly quit. Please re-record your video. So if I sound like I'm mentally defeated, I am. I really don't want to do this again, but here we are. So in the video that you did not see because it did not record, which I am now re-recording, aka this video, what I'm going to do is kind of repeat what I did as the last example in the last video that you saw, where we figured out the slope of the tangent line, not the secant line, but the tangent line, by calculating the slope of the secant line, aka the average rate of change, when the 2 points that define the secant line are some number, like the number 3, and an expression, that same number 3 plus h. And that seems really weird. It's unexpected that the slope of the secant line from 3 to 3 plus h has anything to do with the slope of the tangent line at 3. But really what you end up doing is a bunch of algebraic manipulation, and then you make the observation that when h approaches 0, these 2 points both approach 3. This one's already 3, and this one, if h is close to 0, is approaching 3. And as we saw in a previous video, secant lines approach tangent lines as the 2 points that define the secant line converge. So when h approaches 0, the slope that the secant line approaches is the slope of the tangent line. And I know that's asking a lot to make that connection right now, but really the important thing, the purpose of this video, is not necessarily to understand all those theoretical ideas beneath this stuff, although it'd be awesome if you did, but rather just to understand the algebraic tricks necessary to evaluating these expressions as h approaches 0. And it turns out that what's necessary to evaluate these expressions as h approaches 0 is to cancel out the h in the denominator. And canceling out that h in the denominator can be fairly easy, I guess, as it was in the last video, or it can be really hard and involve some complicated algebraic techniques, as it's going to in this video. The good news is there aren't infinitely many of these techniques. For the purposes of our class, you're going to need to be able to cancel out that h that I'm talking about in the denominator in 3 different cases. When you have a polynomial, like we saw in the last video, and then also when you have a rational function, something that kind of looks like this, and when you have a radical function, something that kind of looks like this. So I'm going to show you the tricks for those latter 2 cases, and you'll apply those tricks on very similar looking functions in the homework, and you'll know everything that you need from this section. So without further ado, let's figure out the average rate of change. So when I say average rate of change, hopefully you're thinking slope of secant line. And when you're thinking about secant lines, hopefully you're thinking, oh, I need 2 different points to define my secant line. And fortunately, we're given 2 different points. Maybe we call them x1 and x2, where x1 is equal to 4 and x2 is equal to 4 plus h. And I know it's kind of weird that these aren't both numeric, like 4 and 7. They're 4 and 4 plus h, but that's fine. You do the same steps that you would have done if these were both numeric. You figure out y1 and you figure out y2, so that you can plug into this formula for the slope, which is the difference in the y coordinates divided by the difference in the x coordinates. If x1 is 4, I can figure out y1 by putting 4 into this machine by evaluating f of 4. F of 4 is easy enough, just copy exactly what you see written here, except you change all the x's into 4's. So I get 2 divided by 4 minus 3. I get 2 divided by 1, I get 2. y1 is equal to 2. x1 is equal to 4. x2 is equal to 4 plus h. All that's left is to figure out y2. y2 is just what comes out of this machine when you put x2 into it. So it's f of 4 plus h. I know it's a little bit weird putting 4 plus h into this machine. It's strange evaluating functions at expressions instead of numbers, but you do it the exact same way. You copy exactly what you're seeing here, except you change all the x's, which signify the input, into 4 plus h's. So I would get 2 divided by 4 plus h minus 3. 2 divided by 4 plus h minus 3 simplifies a little bit. The 4 and the negative 3 net out to positive 1. So I get 2 divided by h plus 1. I got x1, x2, y1, and y2. It's time to come down here to my slope formula and to plug stuff in. y2 minus y1 is going to be this expression, 2 divided by h plus 1, minus this number, 2. x2 minus x1 is going to be 4 plus h minus 4. I want to simplify this expression, which represents the slope of the secant line to this function at these two different points. How do I simplify this expression? Well, first, maybe some low-hanging fruit. Notice that on the denominator, I got 4 plus h minus 4. The 4 and the negative 4 net out, and I'm left with just an h down in the bottom. Hey, that was the same thing that happened in this example, right? The 3 and the negative 3 canceled out, and I was left with just an h in the denominator. Yeah, and that's not a coincidence. That's going to happen in all of these problems. Anytime you're figuring out the average rate of change, when one of the x values is a number and the other one is that same number plus h, when you take the difference in those two x coordinates, the numbers are going to cancel out and you're going to be left with just the h. It's not a coincidence that I have an h here and that I also had an h right here. In fact, I'm also going to have an h in this expression in the denominator as I simplify the average rate of change. But I don't want to get too far ahead of myself. What I want to do is simplify the numerator here. 2 divided by h plus 1 minus 2. How do you simplify that? Well, I don't need you to know how to simplify that. What I'm going to do is demonstrate how to simplify that. What I need out of you is to be able to recreate what I'm doing when you see a problem like this on the homework. So what am I going to do? What I'm going to do is I'm going to try to make this all one fraction up top. Right now it's a fraction minus a whole number, the number 2. What I want is for this to all be one fraction. Well, the first comment is it's kind of hard to subtract a whole number from a fraction. It's a lot easier to subtract two fractions. So what I'm going to do is I'm going to change this 2 into a fraction. How do I change a 2 into a fraction? Just rewrite it as 2 divided by 1. Right, 2 divided by 1 is the same as 2, but the advantage of writing it this way is now it looks like a fraction. And I have methods for subtracting fractions. My first step is just change the 2 into a 2 divided by 1. My second step is to subtract those two fractions. Okay, that begs the question, how do you subtract fractions? Well, maybe you remember from math way back in the day that the only way you can subtract fractions is if you have a common denominator. And you don't have a common denominator. The denominator here is h plus 1, and the denominator here is 1. How can I make them have a common denominator? Well, I can take this fraction over on the right and multiply the top and bottom of that fraction by h plus 1. Few comments. Make sure you do it to the top and the bottom, otherwise you're changing the value of this thing. As long as you're multiplying the top and the bottom by the same amount, it's like you're multiplying it by 1, so it doesn't change the value. How did I know to do h plus 1 on the top and the bottom? Well, because now on the bottom I got 1 times h plus 1, which is the same as h plus 1. I have a common denominator up here in the numerator. Because I have a common denominator up in the numerator, I can subtract those two fractions. 2 over h plus 1 minus 2 times h plus 1 over h plus 1 is the same as 2 minus 2 times h plus 1 divided by h plus 1. Wait, what just happened there? You have the same denominator, so you only write it one time, and you subtract the numerators, 2 minus 2 times h plus 1. If you don't see it, think like 6/7 minus 2/7. Right, what you do in this case is you'd recognize that since you have the same denominator, you can just subtract the numerators. 6 minus 2 is 4, and you write the 7 a single time. When the denominators are the same, write that denominator once, subtract the numerators. That's what I did over here. I wrote the denominator one time, that's that h plus 1, and I subtracted the numerators, 2 minus 2 times h plus 1. If you have a hard time following this algebra, maybe this example of arithmetic will help you. Anyways, that's all just dealing with the numerator. I still have this h down in the denominator here. It doesn't look like I'm getting anywhere, but this is a lot closer to done than it was before, because now I just have a single fraction up in the numerator. In fact, I can simplify that single fraction a little bit. I can get rid of these parentheses by taking the negative 2 and distributing it through. Be careful not to distribute a positive 2. Make sure you distribute a negative 2. So if I take the negative 2 and distribute it through, I would get 2 minus 2h minus 2 up in the top of my numerator. And in the bottom, I would just have the h plus 1. And then don't forget that I still have this h hanging out, waiting for later down in the denominator. Staring at the numerator up here in the top, this 2 and this negative 2 can cancel out as I combine like terms. So this fraction up in the numerator is really just negative 2h divided by h plus 1. And then down on the bottom here, I have this h, but I don't want to just write it as an h. I want to write it as a fraction. So the same way I rewrote this 2 as 2 over 1 to make it a fraction, I'm going to rewrite this h as h over 1 to make it a fraction. My goal all along was to simplify this expression. Simplify in this case means get rid of the fractions inside fractions. How do you get rid of fractions inside fractions? You make it a single fraction divided by another fraction, which we've now done. You may recall from a previous class that the way you divide fractions is you multiply by the reciprocal of the denominator. So instead of negative 2h divided by h plus 1 divided by h over 1, I'm going to write it as negative 2h over h plus 1 times 1 over h. Think about dividing by 3 is the same as multiplying by 1/3 if you want. The way you divide fractions is you multiply by the reciprocal of the denominator. In other words, flip the bottom part upside down. Nice thing happens when you flip the bottom part upside down. The h up here in the numerator and this h cancel out. And I'm left with just negative 2 divided by h plus 1. Couple of comments. Students want to cancel out this h and this h, for example. But you can't do that. The reason you can't cancel out these h's is because you have multiple terms here. You can't cancel over addition and subtraction. But what I really have here is h plus 1 times h down on the bottom and negative 2 times h up on the top. And I can cancel over multiplication, so this h and this h can cancel, even though this h and this h cannot cancel. It's easy to get lost in what we're doing, but what we just did was accomplish our goal. This expression right here represents the slope of the secant line to this curve from 4 to 4 plus h for any value of h. So if you wanted to know the slope of the secant line from, 4 to 5 maybe, all you'd have to do is change all the h's into 1s, because 4 plus 1 is 5. So you'd come down here and you'd be like, well, if h is 1, I'd have negative 2 divided by 1 plus 1. I'd have negative 2 over 2. I'd have negative 1. The slope of the secant line from 4 to 5 is just negative 1. But you don't care about the slope of the secant line from 4 to 5. What you want is the slope of the tangent line. But look, as h approaches 0, negative 2 over h plus 1 is going to approach negative 2. Because if h is really close to 0, 0 plus 1 is close to 1, and negative 2 divided by 1 is just negative 2. As h approaches 0, the slope, the m, approaches negative 2. And that realization is key. Because as h approaches 0, these 2 points approach each other. And as we've seen before, when the 2 points that define the secant line converge, the secant line approaches the tangent line. So the way we're going to calculate the slope of the tangent line is by looking at the behavior of the secant line when the 2 points converge, in other words, as h approaches 0. Because of this realization that I have squared in this box here, we know that the slope of the tangent line to this function at x equals 4 is negative 2. I'm really fighting 2 different battles here. I'd like you to understand kind of the theoretical side behind these calculations, understanding why we want h to approach 0, understanding how that changes the secant line into a tangent line. But if you're not there yet, that's okay. I know the theoretical side of this is really challenging. What I want to make sure that you have right now is the algebraic skills to come up with this negative 2, to simplify this slope expression that you see right here into this slope expression that you see right here. And I think that that's pretty challenging. What it involves is some algebraic tricks, specifically simplifying fractions inside fractions. The good news is the way that you will do this in this class will always be following these same steps that I did in front of you. In the denominator, you'll always just have the letter h. In the numerator, you'll always have 2 different fractions. They might show up as fractions immediately, or they might be fractions and whole numbers. But either way, you can make them fractions minus fractions. Then you can then get a common denominator so that you have a fraction divided by a fraction, at which point you'll employ this little trick that the way you divide fractions is you multiply by the reciprocal of the denominator. And if you do all your algebra perfectly, you'll always be able to cancel out this h, which shows up right here in my expression. And once this h is gone, you'll be able to think about the behavior of this thing as the h approaches 0 without dividing by 0 and getting an undefined output. The good news is anytime you have a rational function, it's going to feel a lot like these steps that have been demonstrated for you. The bad news is you're not always going to have rational functions. Sometimes you're going to have polynomials. Yeah, that's okay. You showed me how to do that already. Okay, but sometimes you're going to have radical functions. It's going to look like this. And the tricks that we've learned here in blue and up here in pink aren't going to help you at all. There's a new trick that you need to know. So what I want to do is show you that new trick and then be done with this video for the second time and hope that it actually records this time. Let's figure out the average rate of change of this function, f of x equals 2 times the square root of x plus 5, from 4 to 4 plus h. Let's come up with the slope of the secant line when the 2 points that define the secant line are 4 and 4 plus h. We'll let x1 be equal to 4, and we'll let x2 be equal to 4 plus h, and we'll recognize that all we need to use this formula, where m is equal to y2 minus y1 over x2 minus x1, our familiar slope formula, is figure out what y1 and y2 are equal to. y1, that's easy. That's just what comes out of this machine when I put x1 into it. It's just f of 4. What's f of 4? Copy exactly what you see here, changing all the x's into 4's. It's 2 times the square root of 4 plus 5. The square root of 4 plus 5 is the same as the square root of 9, and the square root of 9 is 3. 2 times 3 is equal to 6. x1 equals 4, y1 is equal to 6. When I put 4 into this machine, 6 comes out. If I were to graph this machine, I would see that it goes through the point 4, 6. What I really want to know is the slope of the tangent line to that graph at that point 4, 6. And the way I'm going to figure that out is kind of a roundabout way. I'll be like, I don't know how to calculate the slope of a tangent line because tangent lines only involve 1 point, and I need 2 points to calculate slopes. So what I'm going to do is not focus on the tangent line, but instead focus on the secant line. For the secant line, I need 2 different points. One of them is 4, and the other one, totally different, 4 plus h. What's h? Don't worry about that. It's just a variable that represents the difference between my 2 different x values. So if it were the secant line from 4 to 10, h would be equal to 6. x2 is 4 plus h, y2 is just what comes out of this machine when I put 4 plus h into it. To figure out what that is, I copy exactly what I see written here, except I change all the x's into 4 plus h's. So I get 2 times the square root of 4 plus h plus 5. y2 is 2 times the square root of 4 plus h plus 5. Could stop there, but you might as well combine like terms and recognize that 4 plus 5 gives me 9. So it's 2 times the square root of 9 plus h. And you're like, oh yeah, and the square root of 9 is 3, so let's cancel out somehow and simplify. No, you can't do that because you have multiple terms under the radical here. You can't simplify the square root and the 9. It's kind of the same idea as not being able to take this 2 and distribute it and make it 9 plus h. The reason you have to do FOIL here is because you can't take exponents and distribute them to multiple terms. It's really the same idea going on down here. This is 9 plus h to the 1/2 power. That's what it means to take the square root of something, is you're raising it to the 1/2 power. And you can't take that 1/2 power and distribute it to the 2 terms because there's 2 different terms. You can't simplify this expression the way it's written. So what do? You just go plugging into your slope formula. The slope formula is y2 minus y1 over x2 minus x1. And I now have y2, y1, x2, x1. So I just go plugging in. I got 2 times the square root of 9 plus h minus 6 divided by 4 plus h minus 4. Note that just like we've seen in the previous 2 examples, there's some low-hanging fruit. In the denominator here, this positive 4 and this negative 4 cancel, and I'm left with just an h. That's not a coincidence. That's always going to happen. Same thing that we saw up here. That h, which will always show up as the problematic h, it's the one that you need to cancel out so that you can do this analysis. Think about this h maybe in a different color. This one's pink instead of red or something, and that's the one that's got to go. To get rid of that h, there better be an h up in the numerator I can cancel it out with. You're like, well, there's this h right here, right? I got 2 times the square root of 9 plus h minus 6. How about I just go kind of canceling these out? No, absolutely not. You can't do that because this h is underneath a radical for one reason. You also can't do it because you have multiple terms because of this minus sign up in the top. There's lots of reasons why these h's do not cancel out. Okay, if that's what I can't do, why don't you tell me what I can do? Well, there's a little trick. Here's the trick that you shouldn't know that I'm going to demonstrate to you, and hopefully you can follow it so that when you come up in an example that looks very similar to this, you can employ this trick. The trick is what's called multiplying by the conjugate. What is the conjugate? The conjugate is something that exists when you have 2 terms. In this case, the 2 terms are 2 times the square root of 9 plus h, that's my first term, and 6, that's my second term. The terms are the things separated by plus and minus signs, in this case a minus sign. So what I want to do is look at the top here and see those 2 terms. Here's one of them, here's the other one. To come up with the conjugate, I copy those same 2 terms. I'm going to write them in these parentheses, except I change the sign in between the terms. So what I'm saying is I'm going to write exactly what I see here, 2 times the square root of 9 plus h, my first term. And then I'm going to write exactly what I see over here, the 6, my second term. But what I'm going to do is I'm going to change the sign in between those two terms. So in this case, it was a negative. So what I'm going to do is write a positive right here. If this were already a positive, I would have written a negative over here. The conjugate of these two terms is almost the exact same thing as these two terms. The only difference is you change the sign in between them. You don't change the sign underneath the radical because that's all part of this first term. You just change the sign in between the two terms. In this case, from negative to positive. What's written in pink here is the conjugate of what's written in red right here. If I'm going to multiply the top of this fraction by this conjugate, I better also multiply the bottom of the fraction by this conjugate, because if I don't multiply the top and the bottom by the exact same thing, I'm changing the value of that fraction. And I don't want to change the value of this fraction. I just want to rewrite it in a different equivalent form. The trick to simplifying radical expressions in these average rate of change problems is this conjugate trick. And you shouldn't know this conjugate trick until it's demonstrated for you. But now that it's been demonstrated for you, hopefully you can recreate it. At this point, you're like, okay, I think I can recreate it, so I'm done? No, not even close. I mean, if you look at this thing, it's a huge mess. You could argue it was a lot prettier up here than it was down here. However, this is neater than it might seem. Multiplying by a conjugate works out really nicely mathematically. Because think about what you'd have to do here. If you were multiplying these two terms times these two terms, you'd have to think FOIL, right? You'd have to multiply the first terms, so this times this, then the outer terms, so this times this, then the inner terms, and then finally the last term. There'd be 4 different steps required to multiply these terms times these terms. But because these two terms are so similar to these two terms, that process of multiplying the different terms is going to work out really nicely. Let me demonstrate. First, the f in FOIL. 2 times the square root of 9 plus h times 2 times the square root of 9 plus h. So I have 2 times square root of 9 plus h times 2 times square root of 9 plus h. 2 times 2 is equal to 4. And the square root of 9 plus h times the square root of 9 plus h is saying the square root of 9 plus h squared. And the square root and the square cancel out, so I get 4 times 9 plus h. That's just the f in FOIL. We still have to do the o, the I, and the l in FOIL, but a nice thing happens with the o and the I. Look at what happens when I take 2 times the square root of 9 plus h times the 6. 2 times 6 gives me 12, so I get 12 times the square root of 9 plus h. You're like, I don't see what's so nice about that. We'll move on to the next step. The next step would be negative 6 times 2 times the square root of 9 plus h. Instead of taking positive 6 times this 2 times the square root of 9 plus h, I take negative 6 times this 2 times the square root of 9 plus h. I'm going to get almost the exact same thing that I have here, except instead of it being positive, since it's a negative times a positive, it's going to be negative. I get negative 12 times the square root of 9 plus h. The o and the I in FOIL are almost identical. One of them's positive and one of them's negative. So those are going to cancel out. And that's nothing special with this function. That's going to always happen when I multiply by the conjugate, which is why I chose the conjugate in the first place. It makes things simplify really nicely. This was the f in FOIL. This was the o, the I. What's left is the l. The negative 6 times the positive 6 is just negative 36. It looks like things are blowing up and getting really ugly, but when I combine like terms, this and this is going to cancel out, and the top is a lot nicer than it actually looks. In the denominator, it's tempting to get rid of these parentheses, but don't. Just copy exactly what you see in the denominator, h times 2 times the square root of 9 plus h plus 6. Why don't you want to get rid of the parentheses? Well, either because just trust me and don't do it, or because this h was kind of the bad h that you were trying to get rid of. And if you take that h and distribute it through the parentheses, then it's going to show up twice, and you're going to have more work to do to cancel it out. Leave it factored out here by itself so that you can cancel it with an h up in the numerator. That was the tricky step. From here on out, the algebra isn't nearly as bad. I'm not saying it's not bad, it's just not as bad, right? I got positive 12 9 plus h, negative 12 9 plus h. Those cancel out. If I want to get rid of these parentheses, 4 times 9 and 4 times h would give me 36 plus 4h, and then I'd have this minus 36. Maybe you can see how if you cancel out these terms and distribute this 4, when all the dust settles in the numerator, you get 36 plus 4h minus 36. I'm going to leave the denominator completely alone for now, and recognize that if I combine like terms up in the numerator, this 36 and this negative 36 will net out to 0, and I'll be left with just 4h divided by h times 2 times the square root of 9 plus h plus 6. An awesome thing just happened. Up in the numerator, I only have one term, and that term has an h in it. In the denominator, this h is factored out, so I can cancel this h and rewrite this expression as 4 divided by 2 times the square root of 9 plus h plus 6. It might not seem like this line is that different from this line, but it's hugely different from this line because this h is now gone. And this h was the problematic h, because remember, our goal all along is to think about what happens to this slope as the h approaches 0. And now that this h is gone, we can do that analysis. If this h is still here, then when we try to change all the h's into zeros, we divide by 0 and we get stuck with an undefined output. But now that that h is gone, I can look at this and say, as h approaches 0, let's see what would happen to this slope. I would have 9 plus 0, which would just be 9, which I can then take the square root of. The square root of 9 is just 3. So m would approach 4 divided by 2 times the square root of 9, that 3, plus 6. 2 times 3 is 6, plus 6 more is 12. So I get 4 over 12, in other words, 1/3. As h approaches 0, m approaches 1/3. That's really important. What that means is by using the slope of the secant line, I figured out the slope of the tangent line. And the slope of the tangent line to this function f of x when x is equal to 4 is just equal to 1/3. Again, following the theory behind this stuff with secant lines and tangent lines is great. But if you don't get that all right now, it's okay. We're going to be doing that for the next couple of sections. What I want to make sure that you have now is this algebraic trick, this multiplying by the conjugate, to allow you to simplify this expression so that it gets to this form. There's a different trick in this example as there was in this example, and each of those tricks differ with the trick that you've seen in this example. But if you can understand those 3 different tricks, you'll know all the tricks necessary for any of the functions that we're dealing with at this point in the class.